Alright, so this video we're going to talk about rational functions and graphs of rational functions. The general form of all rational functions is f of x equals two polynomial functions, the ratio of two polynomial functions, p of x and q of x. And the key thing here is that the denominator, which is the polynomial q of x, cannot be zero, cannot be equal to zero. That's the general form of them. You have the ratio of two polynomials, or as a fraction. Rational functions, they produce some pretty interesting graphs here, and in some of these graphs they're going to have asymptotes, or they could have asymptotes. And those are lines that the graph of a function will approach. There are three types of asymptotes. First one is a vertical asymptote. That occurs at any value of x where the denominator is 0. So if you can solve for x in the denominator and get x equals 1 or x equals 2, that's going to be your vertical asymptote. Horizontal asymptotes occur when the degree of the numerator and denominator are the same. When they're the same, we take the ratio of the leading coefficients. Again, for horizontal asymptotes, the degrees of both the numerator and denominator have to be the same, and in that case we take the ratio of the leading coefficients of the numerator and the denominator. And then an oblique or a slant asymptote, that only occurs when the degree of the numerator is one more than the degree of the denominator. Something interesting here is that a graph can have a vertical and a horizontal asymptote, but it can never have both a vertical and a horizontal and oblique or slant asymptote. It'll either have a horizontal asymptote or it'll have an oblique or slant asymptote. It won't have both of these in the same graph. And then holes, these functions can produce something called holes. Those occur when the numerator and denominator have a common factor. So if you can factor the numerator and denominator and get, say, a common x plus 3, that'll simplify out of the function, and wherever x plus 3 equals 0, that's where the hole will occur. So first off, first example here, we have the function f of x equals 6 over x plus 2. The very first thing that we notice here is what value of x makes the denominator 0. Well, if we do x plus 2 equals 0, well, x cannot be negative 2. This right here is our domain restriction on x. Ironically enough, this equation here, x equals negative 2, is going to be our vertical asymptote. That's going to be our vertical asymptote. Right. Now, what we also should know, since this degree in the numerator is 0 and this degree is 1, right, there's going to be a horizontal asymptote right at the x-axis. So since the degree of the numerator is 0 and degree of the denominator is 1, the horizontal asymptote is at y equals 0. Right? So if we were to actually go ahead and graph this on an xy axis, all right, make this a little bit bigger here. we established we're going to have a vertical asymptote at x equals -2. So that's going to be right here. And a horizontal asymptote at the y-axis. I'm not going to actually draw it because I don't want to mess my blue marker up. Okay? Now, the way we're going to graph these, there is no clear-cut shortcut to doing this. We have to actually take values of x and substitute it in. So what we're going to do is we're going to go x and y, and we're going to pick intervals that are less than -2 and intervals that are greater than -2. So let's pick when x is -3. Well, what is y when x is -3? Alright, take your calculator, do 6 divided by the quantity -3 plus 2, and you'll get -6. So that point here is going to be somewhere all the way down here if we were to keep extending this line down. We have -1, 2, 3, 4, 5, 6. That's going to be right about there. If we did -4, we get 6 divided by -4 plus 2. That's going to be -3. So when x is -4, that's going to be -3. If we pick, say, -5, we get 6 divided by -5 plus 2. That's going to be -2. Right here, we pick, say, -7, or if we pick, say, -8, we get 6 divided by -8 plus 2. That's going to be -1. That'll be right about there. And this graph here is going to connect through these points and go just like that. Alright, that's going to be what that part of that graph looks like. Now let's look on this side of the vertical asymptote. Alright. And let's pick values of x that are greater than -2. So let's try -1. So 6 divided by -1 plus 2 is +6. So if we extend here, we get -1, -6. If we go with 0, we get 3. So right here, if we pick 1, we get 2. Then if we pick 4 per se, we get 1, which is right here. Then we can connect these points as well. Now, the interesting thing here is these lines here that are these lines here that are graphs that we use using the table of values. This vertical asymptote, the graph here will never ever hit it. It'll get really close to it, but it'll never actually touch it. Same thing with the horizontal asymptote. If we had it drawn here, you would see that it would almost glide right by it. It would never touch it, but it would glide right by it. And this right here is the graph of the function f of x equals 6 divided by x plus 2. That's what the graph will look like. All right. We could also state end behavior here if we wanted to. We could say as x gets larger, as x gets infinitely smaller, it tends to drift toward the value of f of x. Behaves like 0, and as x gets larger, f of x seems to trend towards 0 as well. And then we could talk domain and range. The domain here, all values of x that aren't -2. So we could say our domain is x cannot be -2, and our range is y cannot be 0, or f of x is not 0. If you're in a calculus course, you actually use limits to say that as x gets closer to -2 from the left and the right side, you'll notice it gets it either goes to -infinity or +infinity. Right? But that's what the graph of that looks like in a nutshell. There is no clear-cut way to graphing these. Using a shortcut, you actually have to produce a table of values in order to graph them. Alright, second example here. Let's graph the function f of x equals 3x cubed, or 3x squared. Alright, let's look at a second example here. Let's graph this function f of x equals 3x squared minus 3 divided by x squared minus 9. But you'll notice the degrees of the numerator and denominator are equal. Since the degree of the numerator and the denominator is the same, our horizontal asymptote again, because the degrees are the same, is the ratio of the leading coefficients here, which is 3 divided by 1. So our horizontal asymptote, that's a horizontal line. Horizontal lines are modeled by y equals 3 divided by 1, which is 3. Now for our vertical asymptotes, those are values that make the denominator 0. So if we do x squared minus 9 equals 0 and solve it for x, we get x squared equals 9, take the square root, and we get x equals plus or minus 3. So our vertical asymptotes, in this case we have two of them, are going to be at x equals -3 and x equals +3. So in our graph here, if we have a coordinate plane, our horizontal asymptote, y equals 3, it's going to be right here. And our vertical asymptotes are going to be at x equals -3, so right here. And right here. So now this graph is going to be in one of these two regions, one of these two regions, and one of these two regions. We will use a table of values for each. Alright, we will use a table of values for each, and we'll say x, y. Let's pick x equals -4. Alright, when x equals -4, when x equals, say, -4, we will get about +6.4. When x is -5, we'll get about 4.5. When x is negative 6, we'll get about 3.9. And when x is negative 7, we'll get about 3.6. And if we graph them, negative 4, 6.4, that's about right here. Negative 5, 4.5, that's about right here. 6, 3.9 is about right here. And negative 7, 3.6 is about right here per se. And there's that part of the graph. Now if we go on this interval here, we can pick negative 2, and we get about negative 1.8. Negative 1 we get 0. At 0 we get about 0.3. At 1 we get 0, and at 2 we get about negative 1.8. So when we graph them, x equals negative 2, we get about negative 1.8, that's about right there. Negative 1 we get 0, 0 we get about 0.3. At 1 we get 0, and then at 2 we get negative 1.8 again. So this graph comes up, down, like that. That part goes like that. And you might be thinking, okay, since this is rising up like that, you might want to say it's symmetric with respect to the y-axis. And indeed, you're going to be right. But let's go ahead and just show that real quick. If we pick positive 4, we get about 6.4. 5, we get 4.5. 6, we get 3.9. And 7, we get about 3.6. And we can pretty much mirror these points here as well. And there's your graph of f of x equals 3x squared minus 3 divided by x squared minus 9. Okay? So, again, no clear cut, no shortcut to graphing these. For the asymptotes, those are probably the easier part, but for the actual graphing, you need to use a table of values. What I'm doing is I'm using my graphing calculator to come up with this table of values. You should do it algebraically to come up with them as well. So there's that graph of f of x equals 3x squared minus 3 divided by x squared minus 9.